Welcome to this coding challenge. In this problem, titled Prime Arrangements, we'll explore an interesting way to arrange numbers from 1 to n. The challenge requires us to position prime numbers at prime indices and non-prime numbers at non-prime indices. Let's dive in and solve this step by step. The problem asks us to determine the number of ways to arrange the first n positive integers such that prime numbers occupy prime indices and non-prime numbers occupy non-prime indices. To clarify, the indices are 1-based, meaning the first position is index 1, the second position is index 2, and so forth. Since the total number of permutations can grow very large, the result must be returned modulo 10⁻9 plus 7. The input to the problem is a single integer n, which can range from 1 to 100. The output is the total number of valid arrangements that satisfy these conditions. For example, if n is 5, the answer is 12. This is one of the examples we will explore further to understand the reasoning and calculations behind it. To explain the example where n equals 5, the first 5 positive integers are 1, 2, 3, 4, 5. Among these, the prime numbers are 2 and 3. Their corresponding indices, based on a 1-based index system, are positions 2 and 3. The non-prime numbers are 1, 4, and 5, which correspond to indices 1, 4, and 5. To create valid permutations, we must ensure that primes like 2 and 3 are only placed in the prime indices, and the non-primes like 1, 4, and 5 are placed in the non-prime indices. The number of ways to arrange the primes is 2, which equals 2, and the number of ways to arrange the non-primes is 3, which equals 6. When we multiply these two values, we get the total number of valid permutations for n equals 5, which is 2 * 6 equals 12. This demonstrates how the factorial of the prime count and non-prime count plays a key role in solving the problem. In the case of a larger input, such as n equals 100, there are a total of 25 prime numbers among the first 100 integers. These include numbers like 2, 3, 5, 7, and so on, up to 97. The remaining 125 equals 75 numbers are non-prime. To calculate the total number of valid arrangements, we first compute the factorial of the prime count, which is 25, and the factorial of the non-prime count, which is 75. Multiplying these two values gives the total number of permutations, but since these values are extremely large, we take the result modulo 10⁻9 plus 7. For n equals 100, the final output is 6822891015. Additionally, the constraints of the problem specify that n can range from 1 to 100, and the output must always be returned modulo 10⁻9 plus 7. For edge cases, if n equals 1, there are no primes, so the single number is trivially arranged in one way. For cases like n equals 4, where all numbers are non-prime, there is only one valid arrangement as well. For larger values of n, efficient computation of factorials and modular arithmetic is crucial to avoid overflow and ensure correctness. To solve this problem, we need to arrange numbers from 1 to n in such a way that prime numbers occupy positions corresponding to prime indices, while non-prime numbers occupy non-prime indices. The goal is to calculate the total number of such valid arrangements, and since the numbers can grow large, we take the result modulo 10 to the power of 9 plus 7. Now, the first key observation is that we need to identify prime numbers, which are greater than 1 and divisible only by 1 in themselves. Let the count of such primes up to n be denoted as p. The positions 1, 2, 3, 5, etc. represent prime indices, and the number of these indices corresponds to the same count, p. Once we know the prime and non-prime counts, we can calculate the total arrangements. The prime numbers can be permuted in p factorial, or p ways, and the non-prime numbers in n_p ways. Thus, the total number of arrangements becomes p multiplied by np. To solve the problem, we focus on two key tasks: first, efficiently counting prime numbers up to n, and second, computing the factorials while taking modulo 10 to the power of 9 plus 7 to handle large values. When considering approaches to solve this, we can start with a brute force method. The idea here is simple: loop through all numbers from 2 to n and check whether each number is prime by verifying divisibility by all integers up to its square root. Once we count the primes, we compute the factorials for both the prime and non-prime counts to get the final result. However, this method has a significant drawback. Checking primality for each number is computationally expensive, with a time complexity of O, n asterisk sqrt, n, and the factorial computation adds another O, n, overhead. This quickly becomes infeasible for large values like n equals 100. To address this inefficiency, we can use the sieve of Eratosthenes, a well-known algorithm for efficiently finding all primes up to n. The sieve works by marking the multiples of each prime as non-prime, leaving the primes unmarked. This approach reduces the primality check time complexity to O, n log n, making it much faster. Once we have the count of primes, we can compute the factorials modulo 10 to the power of 9 plus 7. The combination of the sieve and modular arithmetic gives us an optimized solution that's suitable for larger values of n. The optimized approach using the sieve of Eratosthenes is chosen because it efficiently handles the task of counting primes, which is the most computationally expensive part of the problem. The sieve initializes a Boolean array where each index represents whether a number is prime. Starting from 2, it marks all multiples of each prime as non-prime, leaving only the primes marked as true. The total count of true values gives us the number of primes, p. Once we have this count, the next step is to compute the factorials for both primes and non-primes modulo 10 to the power of 9 plus 7. This ensures that the numbers remain manageable and within the problem's constraints. The implementation is straightforward. We define a helper function to count primes using the sieve and another to compute the factorial modulo the specified value. Finally, we calculate the result as the product of the two factorials, taking modulo 10 to the power of 9 plus 7. This approach is both efficient and scalable, making it the best choice for solving the problem. When comparing the two approaches, the brute force method is simpler to implement but becomes inefficient for larger values of n due to its high time complexity. In contrast, the sieve of Eratosthenes, while slightly more complex to implement, scales much better for large inputs. The sieve reduces the primality check to O, n log n, and the factorial computation is straightforward, ensuring the overall solution remains efficient. By combining the sieve with modular arithmetic, we ensure correctness while staying within the problem's constraints. In conclusion, the optimized approach using the sieve of Eratosthenes is the clear choice for this problem. It balances efficiency and scalability, making it suitable for input sizes up to n equals 100, which is the upper limit specified in the problem. This approach not only meets the requirements but does so in a way that guarantees optimal performance. The goal of this problem is to arrange numbers from 1 to n such that prime numbers are placed at positions that are themselves prime indices, while non-prime numbers occupy non-prime positions. To solve this, we need to calculate the total number of such valid arrangements, and since the result can be very large, we take it modulo 10 to the power of 9 plus 7. Now, to break this down, a position is considered a prime index if the index itself is a prime number. For example, positions 2, 3, 5, and 7 are prime indices. Conversely, positions like 1, 4, 6, and 8 are non-prime indices. The problem then boils down to counting how many primes and non-primes we have, and arranging them within their respective categories using factorial permutations. To identify prime indices efficiently, we can use the sieve of Eratosthenes, which calculates all primes up to n in O, n log n, time. This will be the first step in our algorithm. Once we have identified the prime indices using the sieve of Eratosthenes, the next step is to count the total number of prime indices, denoted as p, and the total number of non-prime indices, which would be n minus p. Similarly, we need to categorize the numbers from 1 to n into primes and non-primes. The total number of prime numbers should match the count of prime indices, and the total number of non-prime numbers should match the count of non-prime indices. If these distributions do not align, it means no valid arrangement is possible, and we can directly return 0. Otherwise, we compute the factorial of p to determine all possible arrangements of prime numbers across the prime indices, and the factorial of n minus p for the non-prime numbers. Finally, we multiply these two factorials and take modulo 10 to the power of 9 plus 7 to ensure the result fits within the constraints. When implementing the algorithm, we also need to account for edge cases. For instance, if n equals 1, the result is simply 1, as there is only one number in one position. Additionally, if there are more prime indices than prime numbers, or more non-prime indices than non-prime numbers, it is impossible to create a valid arrangement, and the answer should be 0. To optimize the solution, we use a Boolean array to implement the sieve of Eratosthenes, where each index represents whether the corresponding number is prime. This allows for O1 checks after the initial computation. Another key optimization is pre-computing factorials modulo 10 to the power of 9 plus 7 for all numbers up to n, so that we can retrieve factorial values in constant time during the final computation. These optimizations are crucial for handling larger values of n efficiently. To ensure efficiency, modular arithmetic is used throughout the computation. Since factorial values grow extremely large, we compute them modulo 10 to the power of 9 plus 7 at every step to prevent overflow and maintain manageable numbers. Pre-computing factorials and their modular inverses not only simplifies the main computation but also reduces runtime significantly, as we can rely on quick lookups and multiplications. The overall time complexity of this approach is dominated by the sieve of Eratosthenes, which runs in O, n log n. Factorial pre-computation takes O, n, and the final result computation is O, 1. Space complexity is similarly efficient, requiring O, n, for the Boolean array used in the sieve and O, n, for storing factorials. This makes the solution scalable for the largest inputs allowed by the problem constraints. The implementation follows these steps. First, the sieve of Eratosthenes is used to identify prime indices up to n. Then, we count the number of primes and non-primes within the range, while pre-computing factorials modulo 10 to the power of 9 plus 7. Using these values, we calculate the total number of valid arrangements by multiplying the factorial of the prime count and the factorial of the non-prime count, taking the result modulo 10 to the power of 9 plus 7. Here's the Python code for the entire solution. The function sieve of Eratosthenes efficiently identifies primes, while factorial_mod pre-computes factorials. The main function, count_arrangements, ties everything together by computing prime and non-prime counts, retrieving their factorials, and combining the results. For example, if n equals 10, the function returns the total number of valid arrangements as calculated by these steps. This Python implementation solves LeetCode problem number 1175, prime arrangements. The goal is to calculate the number of valid arrangements of integers from 1 to n such that prime numbers occupy prime indices and non-prime numbers occupy non-prime indices. Here's a step-by-step explanation. First, we define a helper function is _prime, x, to determine if a number x is prime. This function checks divisibility for all integers up to the square root of x. If x is divisible by any number other than 1n itself, it is not a prime. Next, we calculate prime_count, the number of prime numbers between 1 and n, using a generator expression that iterates through the range 1 to n and applies the is_prime function. The count of non-prime numbers is derived as n prime_count. The result is computed by taking the factorial of prime_count and non_prime_count, as these represent the permutations of primes and non-primes respectively. The product of these factorials gives the total number of valid arrangements. Since the result can be large, it is taken modulo 10 to the power of 9 plus 7, as specified in the problem. The solution is efficient and handles edge cases such as small values of n, e.g., n equals 1 or 2, gracefully. The use of the factorial function from the math module ensures the factorial computation is optimized, while the modular arithmetic ensures numerical stability even for large n values. The code is clean, concise, and adheres to best practices for readability and performance. Here, we start by importing the big integer class, which can handle very large numbers, though it will not be directly used in this particular implementation. The main function, numberPrimeArrangements, begins by defining a helper method called isPrime. This method checks if a given number is prime. It first handles the base case where numbers less than 2 are not prime. Then, for numbers 2 and greater, it loops up to the square root of the number, checking divisibility. If any divisor is found, the number is not prime. Otherwise, it is. Next, we initialize a variable, primeCount, to count the number of prime numbers between 1 and n. We iterate through all numbers from 1 to n, using isPrime to determine if each number is prime. If it is, we increment the prime count. After this loop, we calculate the number of non-prime numbers by subtracting primecount from n. This gives us the two key values we need for the final calculation. Now, we define the constant mod, set to 1,000,007,000, which helps us avoid integer overflow by keeping our calculations within this modulo value. Next, we create another helper method called factorial, which computes the factorial of a given number modulo mod. It starts with an initial result of 1 and iterates from 2 up to the given number, multiplying the result by the current number and taking modulo mod at each step to ensure the result remains manageable. With this method ready, we calculate the final result by multiplying the factorial of prime count with the factorial of non-prime count, again taking modulo mod to keep the value within bounds. Finally, we return the result as an integer. This approach ensures efficiency and correctness, even for larger values of n, by leveraging modular arithmetic. In this problem, we need to determine how many valid permutations exist for integers from 1 to n, such that all the prime numbers appear in the first few indices in any order, followed by all the non-prime numbers, also in any order. To achieve this, the result must be calculated modulo 10 to the power of 9 plus 7 to handle large numbers. For example, if n is 5, the numbers from 1 to 5 are 1, 2, 3, 4, and 5. We start by identifying the prime numbers among them. Using an is_prime function, we check each number one by one. Number 1 is not a prime, as it is less than 2. Number 2 is a prime, as it has no divisors other than 1 and itself. Similarly, 3 is a prime. Number 4 is not a prime because it is divisible by 2, and 5 is a prime. This gives us a total of 3 primes, 2, 3, and 5. The remaining numbers, 1 and 4, are non-prime, giving us 2 non-primes. So, the prime count is 3, and the non-prime count is 2. Once we have the counts of primes and non-primes, the next step is to compute the factorials of these counts. Factorials represent the number of ways to arrange a set of items, which is key to solving this problem. For the prime count of 3, the factorial is calculated as 3 times 2 times 1, which equals 6. For the non-prime count of 2, the factorial is 2 times 1, which equals 2. Now, to get the total number of valid permutations, we multiply these two factorials together. 6 times 2 equals 12. Since the problem specifies returning the result modulo 10 to the power of 9 plus 7, we calculate 12 modulo 10 to the power of 9 plus 7, which remains 12. This gives us the final output for n equals 5 as 12. Now, let's look at a larger example where n equals 10. The numbers from 1 to 10 are 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Using the is_prime function, we check the primality of each number. Number 1 is not a prime. Number 2 is a prime. 3 is a prime. 4 is not a prime because it is divisible by 2. 5 is a prime. 6 is not a prime. 7 is a prime, while 8, 9, and 10 are all non-primes. This gives us 4 primes, 2, 3, 5, and 7, the remaining 6 numbers are non-primes. So, the prime count is 4, and the non-prime count is 6. With the counts of primes and non-primes determined, we proceed to compute their factorials. For the prime count of 4, the factorial is calculated as 4 times 3 times 2 times 1, which equals 24. For the non-prime count of 6, the factorial is 6 times 5 times 4 times 3 times 2 times 1, which equals 720. To find the total number of valid permutations, we multiply these two factorials together. 24 times 720 equals 17,280. As before, we take the result modulo 10 to the power of 9 plus 7 to ensure it fits within the problem's constraints. In this case, 17,280 modulo 10 to the power of 9 plus 7 is still 17280. Therefore, the final output for n equals 10 is 17,280. For an even larger example, let's consider n equals 100. Here, we identify the prime numbers from 1 to 100 using the is_prime function. After iterating through all numbers in this range, we find that there are 25 primes and 75 non-primes. Since the factorials of such large numbers grow extremely quickly, we calculate them modulo 10 to the power of 9 plus 7 during the computation to avoid overflow. The factorial of 25 modulo 10 to the power of 9 plus 7 is 440,732,388, and the factorial of 75 modulo 10 to the power of 9 plus 7 is 932,614,679. To get the total valid permutations, we multiply these two values together and again take modulo 10 to the power of 9 plus 7. The result of this calculation is 682,289,015, which is the final output for n equals 100. This approach to the problem hinges on a few key observations. First, the is_prime function determines primality efficiently by iterating only up to the square root of each number, reducing the number of checks needed. Second, since factorials grow extremely quickly, we use modulo arithmetic throughout the computation to keep the results manageable and prevent overflow. Finally, the final result is taken modulo 10 to the power of 9 plus 7 as specified in the problem constraints, ensuring correctness and adherence to the requirements. By combining these techniques, the solution is both efficient and scalable, handling small and large values of n effectively. When analyzing the time complexity of this solution, we can break it into three key components. First, there's the is_prime function, which determines whether a number is prime by iterating up to its square root. This operation takes sqrt x time for each input x. Since we call this function for every number from 1 to n in the list comprehension, the total time complexity for counting primes becomes the sum of square roots from 1 to n. Using the sum of square roots formula, this simplifies to n caret 3/2. Next, we have the factorial computation. To calculate the factorial of a number k, we require k multiplications. In this solution, we compute the factorials of prime_count and non_prime_count, where both counts are at most n. Therefore, the factorial computation contributes n for each, resulting in an overall n time for this part. Combined so far, the prime counting dominates, but we will finalize the analysis as we add the last component. The third component involves modular arithmetic. After computing the product of the two factorials, we apply a modular operation to get the final result. Modular arithmetic is a constant time operation, so it contributes 1. Combining all three components, the overall time complexity of the solution is determined by the prime counting process, which dominates with n caret 3/2. Now, turning to space complexity, the is_prime function uses only 1 space, as it operates with a constant number of variables and does not require additional memory. Similarly, the math.factorial function dynamically handles large integers without requiring extra memory beyond its internal operations, so it also uses 1 space. Finally, the storage of results, such as prime_count and non_prime_count, requires only 1 space. Altogether, the space complexity remains constant at 1. With all components considered, the overall space complexity of the algorithm is 1, as it does not rely on any data structures or memory allocation that scales with the input size n. Comparing this optimized approach to a brute force method highlights its significant efficiency. A brute force solution would involve generating all permutations of the array, which requires n time and filtering prime/non-prime arrangements, making it highly inefficient. It would also require n space to store the permutations. In contrast, the optimized solution avoids generating permutations by directly counting primes and non-primes, and leveraging factorial computations, reducing the time complexity to n caret 3/2 and space complexity to 1. Additionally, because the algorithm always iterates through integers from 1 to n to check for primality and computes two factorials, its time complexity remains invariant across best, average, and worst cases, consistently n caret 3/2. To further justify the big O notation mathematically, we can clearly see that the primality checking dominates the overall complexity. Because the is_prime function iterates up to the square root of each number, summing these square roots up to n gives n caret 3/2, which becomes the primary contributor to the total time complexity. The factorial computations, while linear at n, grow significantly slower than the primality checks, making them secondary in impact. As a result, the total complexity is dominated by the prime counting process, and the overall time complexity of n caret 3/2 is mathematically justified. This balance between the dominating and secondary components ensures that the solution is both optimized and scalable compared to less efficient methods like brute force. When solving this problem, there are some common mistakes to watch out for. First, it's crucial to distinguish between prime indices and prime values. Many mistakenly focus on arranging numbers based on their values being prime, instead of considering the positions, or indices, where those numbers are placed. The problem is about the indices, so always keep that distinction clear. Another common issue is using inefficient or incorrect methods to identify prime numbers. For larger values of n, a naive approach with O(n) complexity can lead to timeouts. Instead, you should use an optimized algorithm like the sieve of Eratosthenes, which operates in O(n) log n time. Additionally, modular arithmetic is essential when dealing with large numbers, especially during factorial calculations. Failing to apply modular arithmetic properly can cause overflow errors or incorrect results. Finally, a lack of pre-computations for factorials and modular inverses can significantly increase runtime. By pre-computing these values, you avoid redundant calculations and improve efficiency. Now, another common pitfall is hard-coding edge cases, such as overlooking scenarios when n equals 1 or 2, or not handling cases where no prime indices exist. Testing these boundaries is a good habit to cultivate to ensure your solution is robust. In interviews, breaking the problem into smaller components is key. For example, separating the identification of prime indices from arranging the numbers demonstrates a structured problem-solving approach. Complexity analysis is another area to focus on. You should be able to explain the time complexity of your solution, such as the O(n) log n, for prime generation combined with O(n) for factorial precomputations. Furthermore, proactively identifying edge cases and explaining how your solution handles them shows attention to detail, which interviewers value. Lastly, modular arithmetic is often a critical part of these solutions, so be prepared to explain why it's necessary and how it ensures calculations stay within bounds. This problem also connects to several related problems that can help deepen your understanding. For instance, LeetCode 31, Next Permutation, focuses on generating permutations in lexicographic order, while LeetCode 60, Permutation Sequence, involves working with specific indices of permutations. LeetCode 204, Count Primes, emphasizes efficient methods for prime number generation, which is directly relevant here. Another related problem is LeetCode 902, Numbers at Most N Given Digit Set, which also deals with constraints on positions and values. As for alternative approaches, you might consider brute force, where you generate all permutations of numbers from 1 to n and filter out the valid ones. While simple to implement, this approach has a factorial time complexity, O(n), which becomes impractical as n grows. A more refined method is backtracking, where you incrementally build arrangements, ensuring primes and non-primes are placed correctly. While backtracking is more efficient than brute force, it still carries a significant overhead due to its recursive nature. The most efficient approach involves factorial precomputation combined with modular arithmetic. By precomputing factorials and modular inverses, you can leverage combinatorics to calculate valid arrangements directly. This method not only handles large inputs efficiently but also avoids the pitfalls of overflow errors thanks to modular arithmetic. The trade-off here is that it requires a solid understanding of both combinatorics and modular arithmetic, which might be challenging for some. However, mastering this technique provides optimal performance and is well suited for competitive programming or interview scenarios. By using this approach, you ensure your solution is both scalable and robust, making it the preferred method for tackling this problem effectively. Great work! We've successfully tackled the prime arrangements problem. Remember, this challenge showcases the importance of primes and their unique properties in programming. Keep practicing, and don't forget to like and subscribe for more problem-solving sessions like this one. See you in the next challenge. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!